First, the record. Between June of 1985 and January of 1987, 6 patients at 4 hospitals received massive radiation overexposures from the same machine. Patients died or were gravely injured. We begin here and keep the camera on the engineering in their memory. The machine was the Therac-25, a radiation therapy machine built to treat cancer. It worked in 2 modes, and the checking that kept those 2 modes safe was done not with steel, but with software. Remember that. In electron mode, it fired a low-current beam. Scanning magnets spread it thin, and a scattering foil shaped it so the dose that reached the treatment plane was gentle and wide. Drawn this way, it is an elegant machine. In X-ray mode, everything changed. The beam ran about 100 times stronger, and it was aimed straight into a heavy tungsten target set in its path, which turns it into a shaped therapeutic X-ray beam. That target was the whole safety of the design. A single rotating turntable carried the right hardware into place. One position for X-ray with the target, one for electron with the magnet and foil, and a third, a bare field light position with nothing in the beam at all, used only to line the patient up with a light. Everything depended on it facing the right way. If you would rather understand why things fail than watch them fail, subscribe. A new failure is drawn here every week, and each one is a reason you are safer than you know. Here is the first flaw, and it is a decision. The earlier Therac machines had independent hardware interlocks, physical circuits that would stop the beam no matter what the software believed. On the Therac-25, those were removed. Software alone now stood between the beam and the patient. Levison and Turner found the software had been carried over from the older machines and trusted because it had run for years, written largely by one programmer with no independent review. And when it faulted, it spoke in codes like malfunction 54 that told the operator almost nothing. Now trace the sequence. The operator types the prescription. A routine called datant hands the mode and energy to another called magnet, which physically swings the magnets into place. Setting those magnets takes about 8 seconds. Here is the race. The operator selects X-ray, then realizes the patient needs electron, moves back up and edits X to E, all inside that 8-second window. The done flag reads finished because the cursor did reach the command line, but magnet has already latched the old state and it will not read the edit. Here is the line. The high current X-ray beam is armed, but the turntable never turned to the X-ray position, so the target is not in the beam. The full beam, the one only tungsten was ever meant to absorb, fires with the target swung out of its path, and the console, reading a beam it cannot explain, reports an underdose. Trained by routine faults to clear them, the operator presses P to proceed, and the machine can fire again. The same defect lived in the older Therac-20, but its hardware interlocks caught it, blowing fuses instead. The difference was the steel that had been taken away. The investigation by Nancy Levison and Clark Turner was precise, and it refused a single villain. The code had run reliably and was still unsafe. Reliability is not safety. Reused code in a machine stripped of its hardware backups was untested in that new place. The FDA declared a Class 1 recall, and it took 5 revisions before the corrective plan was accepted. And here is why the machine at your hospital is safer. The fixes put the steel back, an independent hardware shutdown, and a real turntable position sensor the software cannot override. This became the founding case study of safety-critical software engineering, independent review, and hardware interlocks, later written into standards like IEC 62304. Failure mode, a race condition, and a missing interlock. A high-energy beam, the target retracted, the last hardware stop removed. Nothing breaks without a reason. Now you know this one. Drawing filed. Like and subscribe to support the channel.